Welcome back to Introduction to Logic. This is Unit 5, Natural Deduction in Propositional Logic. In this short video, we'll explore 5 logically equivalent propositions to enhance our ability to prove or demonstrate validity in natural language arguments using propositional logic. In the previous 2 videos, we investigated the 8 rules of inference, which, using truth tables, we demonstrated are really just simple, valid argument forms. We can sort of think of them like Legos, the basic building blocks out of which complex, valid arguments can be built. And just like a set of Legos, each argument has a unique shape or form. Since each argument is valid when we put them all together to make complex arguments, we know that the conclusions of those complex arguments will also have to be valid. But most people don't give us arguments in the form of a proof. Instead, they give us natural language arguments, which hopefully contain valid inferences. But we've learned that by symbolizing the statements in a natural language argument, we can focus more clearly on the logical connections between the premises and the conclusion. So by getting rid of all the words, we basically boil the argument down to its component parts. And then, by applying our inference rules, we can determine whether or not the argument is indeed valid. Here's an example of an argument that's already been symbolized. Now, just looking at this argument, we might intuitively think it's invalid. After all, the elements of the conclusion don't even appear within the premises, so how could that possibly follow validly from the premises? We could, of course, do a truth table and compute all the logical possibilities for these propositions and their logical operators, but that would be rather cumbersome. The inference rules give us a shortcut. We start by doing what we can, and a close inspection of the premises shows us that we have what we need to perform a constructive dilemma. Also note that premise 3 asserts that it's not the case that Q. So we could put that together with line 4, which we just derived, via disjunctive syllogism. We could perform another disjunctive syllogism and prove that Q must be the case. But how does any of this get us any closer to our supposed conclusion? The rule of addition. It allows us to add anything we want, so long as it's in the form of a disjunction, because disjunction tells us that only one of the 2 disjuncts has to be true. And since we've already proven that Q is the case, we can just add S and T. Once again, using disjunctive syllogism, we can now derive S and T, and there it is. We've just demonstrated how this seemingly invalid argument is in fact valid. These simple argument forms, or rules of inference, allow us to peer inside a given argument to determine if the inferences they contain are in fact logically reliable. But what about this argument? It's immediately clear that the conclusion would follow using a constructive dilemma, but I don't have a premise that would allow me to proceed. What I need is a premise in the form of not P or not R, but what I've got is, it's not the case that P and R. Is this argument valid? You'll remember that in Unit 4, we learned that propositions sometimes have logical equivalencies as well as contradictions. What if not P or not R turned out to be logically equivalent to it's not the case that P and R? If that were true, I could simply substitute the premise that I need for the one that I have and proceed to the conclusion. And as it turns out, we'll demonstrate with the truth table below that these 2 propositions are in fact logically equivalent. It's called De Morgan's Law, or De Morgan's Rule, after 19th century logician Augustus De Morgan. With this rule, we could now substitute the proposition that we needed for the one that we had, and then we can see that the conclusion does indeed follow validly from the premises. Logical equivalency allows us to articulate more rules to add to our growing toolbox in propositional logic. And we call these equivalencies rules of replacement, because that's really all we're doing. We're replacing one proposition for another. So long as the two propositions are logically equivalent to one another, we can simply substitute one for the other whenever we need it. So in this video, we're going to explore 5 common logical equivalencies and see how they can help us validate arguments in propositional logic. Now, we've already learned that the negation of any proposition is going to have an opposite truth value. But what would happen if we negated the negation? As we'll see, the negation of a negated proposition will have the same truth value as the original proposition. They are logically equivalent, even though they're actually different propositions. We'll also discover that the conjunctive and disjunctive logical operators will allow us to switch the order of their component propositions. We also learned while doing truth tables that in propositional logic, there is always an order of operations that must be strictly followed. However, when it comes to pairs of disjunctions or pairs of conjunctions, the order can be reversed without changing the truth function of the complex proposition. We've just seen how Augustus de Morgan's insight can be very useful in deductive proofs, but we still have to demonstrate why this rule holds, which we'll do in a minute. Finally, in this video, we'll examine how conjunctions and disjunctions can be put together or taken apart in a distributive rule. We've already learned how to test propositions for equivalency using truth tables, so let's apply those skills to this set of propositions to see what we discover. Now, the easiest rule of equivalence is one that you already know. You learned it back in grammar. But to demonstrate why this rule works, we need to employ a truth table. Since we only have one simple proposition to consider, there will only be 2 logical domains to deal with. There is the world in which P is true, and there's the world in which P is false. Now, with our truth table set up, we can apply the truth values of P across each universe. Next, in order of operations, is to apply the first negation to P, which gives us its opposite truth value. Then we proceed to the second negation. Having completed the computational matrix, we see that the double negative has the exact same truth value in each logical world. This means that P is logically equivalent to it's not the case that it's not the case that P. They're different propositions, but they have the same logical meaning. Since they're logically equivalent, we can substitute one for the other whenever we need it. Having demonstrated the equivalence once, we can simply adopt it now as a rule, just like we did with modus ponens or with constructive dilemma. Now let's see how we might actually use this in the situation of a proof. In this argument, we want to conclude it's not the case that P. Given that the second premise asserts Q, I naturally want to perform a modus tollens to derive not P. However, the argument is not in the correct form to allow me to do that. Modus tollens, you'll recall, requires us to deny the consequent in order to derive a denial of the antecedent. But in this case, the consequent tells me that it's not the case that Q. But premise 2 doesn't deny anything. It is merely asserting that Q. However, since we've just learned the double negative rule, we know that we can substitute the logically equivalent statement, it's not the case that, it's not the case that Q. Now, we would have a denial of not Q, and we can proceed to our conclusion validly using modus tollens. Rules of logical equivalency allow us to replace what we're given in an argument with what we need. Because the statements are logically equivalent, one can always be substituted for the other to allow us to proceed in our demonstration. The next rule we're going to learn is rooted in the logic of conjunction and disjunction. With these two logical operators, and only with these two logical operators, we can reverse the order of the constituent propositions. We've already learned that a conjunction is true on only one condition, when both of the constituent propositions are true. Hence, it doesn't matter which one comes first and which one comes second. And the same is going to turn out to be true in disjunction as well. But let's start with a conjunctive commutation first. Now, once we have the truth table set up and all the truth values filled in for each of the propositions in each of the four possible worlds dictated by having only two propositions, we can determine the truth function of the conjunction of both propositions. We see that in each world of logical discourse, they have exactly the same truth function, which means that these two propositions are logically equivalent. One can be substituted for the other. Now let's take a look at the disjunctive commutation. First, we set up the truth table and fill in all the possible truth values for each proposition in each of the four possible logical worlds. We know that a disjunction will be true whenever at least one of the disjuncts is true. And when we compute the truth functions of each of the propositions in each world, we find that they have identical truth values. So commutativity holds for both conjunctive and disjunctive propositions. Now, let's look at a simple application of the rule of commutation. Here, we want to derive Q from P and Q. Of course, we'll want to apply the rule of simplification. We've already proven that that's a valid argument form, but notice that we can't. We know that we're only allowed to simplify the left-hand conjunct in simplification. And now we're ready to understand why that operational rule applies. Valid arguments are kind of like a chain. Each of the premises must be linked to another premise so that there is never a gap between the premises and the conclusion. This is unique to deductive reasoning. It's completely different in induction. Imagine trying to pull something with a chain, but the hook on the end, your conclusion, wasn't actually linked to any of the preceding links. Your attempt to pull something would be utterly futile. In a valid deduction, there can be no breaks in the chain. Each link must be connected to the next all the way to the end. If we cannot prove each step in the argument, that is, each link in the chain, we can't know that the deduction is going to actually be valid. So now that we know the order of conjunctive propositions can be reversed, we can simply replace premise 1 with its logically equivalent premise 2. Now, we're ready to draw a conclusion, and we've shown why there is no break in the chain of deduction. We have demonstrated each step explicitly, proving that this argument is in fact valid. This, by the way, is the same in mathematics and in algebra, right? Where you're forced to show every step, or if you're doing a proof in geometry, it's exactly the same thing. Each step has to be noted individually, and each one has to be justified by a rule that allows that particular step. What we're seeing in those other mathematical fields is simply an application of exactly what we are doing in a deductive proof. And our rule of commutativity works exactly the same for disjunctive propositions as we've already shown on the truth table. Here, we need to prove why P follows from premises 1 and 2. Of course, we'll want to use disjunctive syllogism, but that rule only allows us to deny the left-hand disjunct. So before we can proceed, we need to substitute the logical equivalence of P or Q, which is Q or P. Now we can proceed to draw our conclusion validly from the premises. Valid deductions require an unbroken chain of necessary connections from premises to conclusion. The argument, as given to us, is like a chain that's all piled up on the floor. What we need to do is find out whether there are any breaks in the chain. That's what we're doing with a proof. We're stretching out the chain and examining each link to make sure that there are actually no breaks in the chain, no gaps between premises and conclusion. Our next rule of logical equivalency is called associativity, and it's going to be easy to see why. All we're doing is changing the association of the component parts of a complex proposition. We know that there's a necessary order of operations in truth tables. We can only calculate one truth function at a time. But it turns out that if we have a pair of disjunctions or a pair of conjunctions, the order can be changed without altering the truth function of the proposition. Imagine three friends go out to get a pizza, and while they're waiting for their pie, they notice that the restaurant has the most excellent of all retro games, Galaga. Now, only one person can play at a time, but two can take turns playing within a single game. That means at least one person will have to wait in order to take a turn. Who will it be? If all three like each other equally, and so long as they each love the game equally, it doesn't matter which pair gets to play the first game. Now we can demonstrate this on our truth table. Having set up the matrix and plugged in all of the possible truth values for each individual proposition, we could now compute the outcome for both associations. We first determine the truth function of the disjunction within the parentheses, and then the truth function of the whole proposition, the main operator. Then we do the same thing for the second proposition. And when we compare the truth function for each, we find that in each universe the outcome is exactly the same, so these two propositions must be logically equivalent. Now we can do the same thing for Street Fighter, where two people can play simultaneously. Again, assuming all things are equal between the friends, it turns out that it doesn't matter which pair gets to play first. The outcome is going to be exactly the same. Now let's apply the rule to an argument. Here we want to prove that Z validly follows from premises 1 and 2. Now we know that we could derive Z via modus ponens if we had R on a line by itself. But in premise 1, it's locked inside the parentheses, and it's on the wrong side of the conjunction in order to simplify. So first, we apply the associativity rule, replacing premise 1 with premise 3. Next, we apply commutation to premise 3. Now we've got R in the correct left-hand position, so we can simplify it out. Finally, we put lines 2 and 5 together in modus ponens, and we can derive Z. So here we see how we can use associativity and commutativity to move the component parts around within an argument to demonstrate that indeed it contains valid inferences, and therefore the conclusion ultimately validly follows from the premises. Now, De Morgan's rule may not appear as obvious as either commutativity or associativity, but it will quickly become apparent. Since a conjunction is only true when both individual propositions are true, the negation of their conjunction tells us that at least one, or possibly both of them, are false. So, if it's not the case that both P and Q is going to be the same as saying either P isn't true or Q isn't true. We can visualize this with our truth table. Having set up the matrix, we compute for the main operator. Once we have the truth function for each determined, we compare them to see that in fact they are identical in all possible worlds. We can do the very same thing for the denial of a disjunction. Again, we find that in all logically possible worlds, these two propositions have identical truth functions. So they're logically equivalent propositions, and we can use them as replacements for each other whenever the need will arise. Consider this example, where we want to prove that S follows validly from the premises. Clearly, we're going to want to use disjunctive syllogism on line 2, but we need to get it's not the case that P on a line by itself. De Morgan allows us to substitute not P and not Q for premise 1. Next, we simplify it's not the case that P from premise 3. Then we can derive our conclusion, S. De Morgan's rule can be a real lifesaver when trying to deconstruct and validate deductive arguments in propositional logic. Now, the last rule we're going to explore in this video is called distribution. With this rule, as with the others we've explored in this video, note that what we are working with is conjunction and disjunction. If we have the conjunction of a proposition to two disjuncted propositions, we can distribute the proposition to the left of the main operator over the operator within the parentheses. The same is going to be true if we have the disjunction of a conjunction. Now, the easiest way I've found to remember this logical equivalency is to think about product supply chains. You have a product in your warehouse and you want to get it to the retailers. So what do? You distribute the product to your customers, who are the retailers. The same works in reverse as well. If you send a defective product to the retailers, you may have to recall the product, bringing it back to the warehouse. Now that we've an intuitive understanding of the distributive rule, let's examine just why it is true using a truth table. First, we complete the truth functions for the disjunction, then for the conjunction. Next, we turn to the proposition that is already distributed and compute the truth functions on that side. With the truth table complete, we can see that in each logically possible world, these two propositions have the same truth function, so we know, we've proven, we've demonstrated that they are logically equivalent propositions. I can substitute one for the other. Next, we can see that the same is going to hold true for the disjunction of a conjunction. Repeating exactly the same process, we compute truth functions until we reach the main operator. And we find the exact same result. So we've now proven that these two propositions are logically equivalent, meaning that we can always substitute one for the other if we need when proving the validity of an argument. Now let's look at a practical example to tie it all together. In this argument, we're trying to prove that Z follows necessarily from premises 1 and 2. It would clearly be easy to derive Z via modus ponens, but we would need P on a line by itself. We can't directly simplify P from premise 1 because it's locked inside parentheses. But we now know that premise 1 is logically equivalent to P and Q or R. By recalling P to the warehouse, we are now in a position to simplify P, and then we let modus ponens do its work, giving us Z. So here's a practical example of the distributive rule, or the rule of distribution. We now have 5 new rules for our logical toolbox, which we can use when we're trying to demonstrate the validity of deductive arguments in propositional logic. Of course, these 5 are not the only pairs of logically equivalent propositions. There are probably countless examples. But having now demonstrated the equivalence of these, we never have to worry about them again. We can just start using them as rules. In our next video, we're going to introduce 5 more common equivalencies, which will give us a total of 10 rules of replacement to use in natural deduction. See you next time.